In the late 1960s, a young Italian physicist named Gabriele Veneziano was searching for a set of equations that would explain the strong nuclear force, the extremely powerful glue that holds the nucleus of every atom together, binding protons to neutrons. As the story goes, he happened on a dusty book on the history of mathematics, and in it, he found a 200-year-old equation, first written down by a Swiss mathematician, Leonhard Euler. Veneziano was amazed to discover that Euler's equations, long thought to be nothing more than a mathematical curiosity, seemed to describe the strong force. He quickly published a paper and was famous ever after for this accidental discovery.
I see occasionally written in books that this model was invented by chance or was found in a math book, and this makes me feel pretty bad. What is true is that the function was the outcome of a long year of work, and we accidentally discovered string theory.
However it was discovered, Euler's equation, which miraculously explained the strong force, took on a life of its own. This was the birth of string theory. Passed from colleague to colleague, Euler's equation ended up on the chalkboard in front of a young American physicist, Leonard Susskind.
To this day, I remember the formula. The formula was and I looked at it and I said, you know, this is so simple, even I can figure out what this is.
Susskind retreated to his attic to investigate. He understood that this ancient formula described the strong force mathematically. But beneath the abstract symbols, he had caught a glimpse of something new.
And I fiddled with it, I monkeyed with it, I sat in my attic, I think for 2 months, on and off. But the first thing I could see in it, it was describing some kind of particles which had internal structure, which could vibrate, which could do things, which wasn't just a point particle. And I began to realize what was being described here was a string, an elastic string, like a rubber band, or like a rubber band cut in half. And this rubber band could not only stretch and contract, but wiggle. And, marvel of marvels, it exactly agreed with this formula.
As Susskind drowned his sorrows over the rejection of his far-out idea, it appeared string theory was dead. Meanwhile, mainstream science was embracing particles as points, not strings. For decades, physicists had been exploring the behavior of microscopic particles by smashing them together at high speeds and studying those collisions. In the showers of particles produced, they were discovering that nature is far richer than they thought.
Once a month, there'd be a discovery of a new particle, the rho meson, the omega particle, the B particle, the B1 particle, the B2 particle, phi, omega. More letters were used than exist in most alphabets. It was a population explosion of particles.
It was a time when graduate students would run through the halls of a physics building, say, they discovered another particle, and it fit the theories, and it was all so exciting.
And in this zoo of new particles, scientists weren't just discovering building blocks of matter. Leaving string theory in the dust, physicists made a startling and strange prediction: that the forces of nature can also be explained by particles.
Now, this is a really weird idea, but it's kind of like a game of catch in which the players, like me, and me are particles of matter.
And the ball we're throwing back and forth is a particle of force. It's called a messenger particle.
For example, in the case of magnetism, the electromagnetic force, this ball would be a photon. The more of these messenger particles or photons that are exchanged between us, the stronger the magnetic attraction.
And scientists predicted that it's this exchange of messenger particles that creates what we feel as force.
Experiments confirm these predictions with the discovery of the messenger particles for electromagnetism, the strong force, and the weak force.
And using these newly discovered particles, scientists were closing in on Einstein's dream of unifying the forces. Particle physicists reasoned that if we rewind the cosmic film to the moments just after the Big Bang, some 14 billion years ago, when the universe was trillions of degrees hotter, the messenger particles for electromagnetism and the weak force would have been indistinguishable. Just as cubes of ice melt into water in the hot sun, experiments show that as we rewind to the extremely hot conditions of the Big Bang, the weak and electromagnetic forces meld together and unite into a single force called the electroweak. And physicists believe that if you roll the cosmic film back even further, the electroweak would unite with the strong force in one grand superforce. Although that has yet to be proven, quantum mechanics was able to explain how three of the forces operate on the subatomic level.
And all of a sudden, we had a consistent theory of elementary particle physics, which allows us to describe all of the interactions, weak, strong, and electromagnetic, in the same language. It all made sense, and it's all in the textbooks.
Everything was converging toward a simple picture of the known particles and forces, a picture which eventually became known as the Standard Model. I think I gave it that name.
Professor Sheldon Glashow, Abdus Salam, and Steven Weinberg.
The inventors of the Standard Model, both the name and the theory, were the toasts of the scientific community, receiving Nobel Prize after Nobel Prize. But behind the fanfare was a glaring omission. Although the Standard Model explained three of the forces that rule the world of the very small, it did not include the most familiar force: gravity. Overshadowed by the Standard Model, string theory became a backwater of physics.
Most people in our community lost completely interest in string theory. They said, okay, that was a very nice, elegant thing, but had nothing to do with nature.
It's not taken seriously by much of the community, but the early pioneers of string theory are convinced that they can smell reality and continue to pursue the idea.
But the more these diehards delved into string theory, the more problems they found.
Early string theory had a number of problems. One was that it predicted a particle which we know is unphysical. It's what's called a tachyon, a particle that travels faster than light.
There was this discovery that the theory requires 10 dimensions, which is very disturbing, of course, since it's obvious that that's more than there are.
It had a massless particle which was not seen in experiments.
So these theories didn't seem to make sense.
This seemed crazy to people.
Basically, string theory was not getting off the ground.
People threw up their hands and said, this can't be right.
By 1973, only a few young physicists were still wrestling with the obscure equations of string theory. One was John Schwarz, who was busy tackling string theory's numerous problems. Among them, a mysterious massless particle predicted by the theory but never seen in nature, and an assortment of anomalies or mathematical inconsistencies.
We spent a long time trying to fiddle with the theory. We tried all sorts of ways of making the dimension before, getting rid of these massless particles and the tachyons and so on. But it was always ugly and unconvincing.
For 4 years, Schwarz tried to tame the unruly equations of string theory, changing, adjusting, combining and recombining them in different ways. But nothing worked. On the verge of abandoning string theory, Schwarz had a brainstorm. Perhaps his equations were describing gravity, but that meant reconsidering the size of these tiny strands of energy.
We weren't thinking about gravity up till that point, but as soon as we suggested that maybe we should be dealing with a theory of gravity, we had to radically change our view of how big these strings were.
By supposing that strings were 100 billion times smaller than an atom, one of the theory's vices became a virtue. The mysterious particle John Schwarz had been trying to get rid of now appeared to be a graviton, the long sought-after particle believed to transmit gravity at the quantum level. String theory had produced the piece of the puzzle missing from the standard model. Schwarz submitted for publication his groundbreaking new theory describing how gravity works in the subatomic world.
It seemed very obvious to us that it was right, but there was really no reaction in the community whatsoever.
Once again, string theory fell on deaf ears. But Schwarz would not be deterred. He had glimpsed the Holy Grail. If strings described gravity at the quantum level, they must be the key to unifying the four forces. He was joined in this quest by one of the only other scientists willing to risk his career on strings, Michael Green.
In a sense, I think we had a quiet confidence that string theory was obviously correct, and it didn't matter much if people didn't see it at that point. They would see it down the line.
But for Green's confidence to pay off, he and Schwarz would have to confront the fact that in the early 1980s, string theory still had fatal flaws in the math, known as anomalies. An anomaly is just what it sounds like. It's something that's strange or out of place, something that doesn't belong. Now, this kind of anomaly is just weird. But mathematical anomalies can spell doom for a theory of physics. They're a little complicated, so here's a simple example. Let's say we have a theory in which these two equations describe one physical property of our universe. Now, if I solve this equation over here and I find x equals 1, and if I solve this equation over here and find x equals 2, I know my theory has anomalies because there should only be one value for x.
Unless I can revise my equations to get the same value for x on both sides, the theory is dead.
In the early 1980s, string theory was riddled with mathematical anomalies kind of like these, although the equations were much more complex. The future of the theory depended on ridding the equations of these fatal inconsistencies.
After Schwarz and Green battled the anomalies in string theory for 5 years, their work culminated late one night in the summer of 1984.
It was widely believed that these theories must be inconsistent because of anomalies. Well, for no really good reason, I just felt that had to be wrong because I felt string theory's got to be right, therefore there can't be anomalies. So we decided we got to calculate these things.
Amazingly, it all boiled down to a single calculation. On one side of the blackboard, they got 496. And if they got the matching number on the other side, it would prove string theory was free of anomalies.
I do remember a particular moment when John Schwartz and I were talking at the blackboard and working out these numbers which had to fit, and they just had to match exactly. I remember joking with John Schwartz at that moment because there was thunder and lightning. There was a big mountain storm in Aspen at that moment. And I remember saying something like, that we must be getting pretty close because the gods are trying to prevent us completing this calculation. And indeed, they did match.
The matching numbers meant the theory was free of anomalies, and it had the mathematical depth to encompass all four forces.
So we recognized not only that the strings could describe gravity, but they could also describe the other forces. So we spoke in terms of unification, and we saw this as a possibility of realizing the dream that Einstein had expressed in his later years of unifying the different forces in some deeper framework.
We felt great. That was an extraordinary moment because we realized that no other theory had ever succeeded in doing that.
But by now, it's like crying wolf. Each time we'd done something, I figured everyone's going to be excited. They weren't. So I figured by now I didn't expect much of a reaction.
But this time, the reaction was explosive. In less than a year, the number of string theorists leapt from just a handful to hundreds.
Up to that moment, the longest talk I'd ever given on the subject was 5 minutes at some minor conference, and then suddenly I was invited all over the world to give talks and lectures and so forth.
New version of string theory seemed capable of describing all the building blocks of nature.
Here's how. Inside every grain of sand are billions of tiny atoms.
Every atom is made of smaller bits of matter, electrons orbiting a nucleus made of protons and neutrons, which are made of even smaller bits of matter called quarks. But string theory says this is not the end of the line. It makes the astounding claim that the particles making up everything in the universe are made of even smaller ingredients, tiny, wiggling strands of energy that look like strings. Each of these strings is unimaginably small. In fact, if an atom were enlarged to the size of the solar system, a string would only be as large as a tree. And here's the key idea. Just as different vibrational patterns or frequencies of a single cello string create what we hear as different musical notes, the different ways that strings vibrate give particles their unique properties, such as mass and charge.
For example, the only difference between the particles making up you and me and the particles that transmit gravity and the other forces is the way these tiny strings vibrate.
Composed of an enormous number of these oscillating strings, the universe can be thought of as a grand cosmic symphony. And this elegant idea resolves the conflict between our jittery, unpredictable picture of space on the subatomic scale and our smooth picture of space on the large scale.
And it's the jitteriness of quantum theory versus the gentleness of Einstein's general theory of relativity that makes it so hard to bridge the two, to stitch them together. Now, what string theory does, it comes along and basically calms the jitters of quantum mechanics. It spreads them out by virtue of taking the old idea of a point particle and spreading it out into a string. So the jittery behavior is there, but it's just sufficiently less violent that quantum theory and general relativity stitch together perfectly within this framework.
It's a triumph of mathematics, with nothing but these tiny, vibrating strands of energy. String theorists claim to be fulfilling Einstein's dream of uniting all forces and all matter. But this radical new theory contains a chink in its armor.
No experiment can ever check up what's going on at the distances that are being studied. No observation can relate to these tiny distances or high energies. That is to say, there ain't no experiment that could be done, nor is there any observation that could be made that would say, you guys are wrong. The theory is safe, permanently safe. Is that a theory of physics or a philosophy? I ask you.
People often criticize string theory for saying that it's very far removed from any direct experimental test, and surely it's not really a branch of physics for that reason. And my response to that is simply that they're going to be proved wrong.
Making string theory even harder to prove is that in order to work, the complex equations require something that sounds like it's straight out of science fiction. Extra dimensions of space.
We've always thought for centuries that there was only what we can see. You know, this dimension, that one, and another one. There's only 3 dimensions of space and 1 of time. And people who've said that there are extra dimensions of space have been labeled as, you know, crackpots or people who are bananas. Well, string theory really predicts it.
To be taken seriously, string theorists had to explain how this bizarre prediction could be true. And they claim that the far-out idea of extra dimensions may be more down to earth than you'd think. Let me show you what I mean. I'm off to see a guy who was one of the first people to think about this strange idea. I'm supposed to meet him at 4 o'clock at his apartment on 5th Avenue and 93rd Street on the 2nd floor. Now, in order to get to this meeting, I need 4 pieces of information. 1 for each of the 3 dimensions of space, a street, an avenue, and a floor number, and 1 more for time, the 4th dimension. You can think about these as the 4 dimensions of common experience. Left, right, back, forth, up, down, and time. As it turns out, the strange idea that there are additional dimensions stretches back almost a century. Our sense that we live in a universe of 3 spatial dimensions really seems beyond question. But in 1919, Theodor Kaluza, a virtually unknown German mathematician, had the courage to challenge the obvious. He suggested that maybe, just maybe, our universe has 1 more dimension that for some reason we just can't see.
Look, he says here, I like your idea. So why does he delay?
You see, Kaluza had sent his idea about an additional spatial dimension to Albert Einstein. And although Einstein was initially enthusiastic, he then seemed to waver and for 2 years held up publication of Kaluza's paper. Eventually, Kaluza's paper was published after Einstein decided extra dimensions were his cup of tea. Here's the idea. In 1916, Einstein showed that gravity is nothing but warps and ripples in the 4 familiar dimensions of space and time. Just 3 years later, Kaluza proposed that electromagnetism might also be ripples. But for that to be true, Kaluza needed a place for those ripples to occur. So Kaluza proposed an additional hidden dimension of space. But if Kaluza was right, where is this extra dimension? And what would extra dimensions look like? Can we even begin to imagine them? Well, building upon Kaluza's work, the Swedish physicist Oskar Klein suggested an unusual answer. Take a look at the cables supporting that traffic light. From this far away, I can't see that they have any thickness. Each one looks like a line, something with only a single dimension. But suppose we could explore one of these cables way up close, like from the point of view of an ant. Now, a second dimension, which wraps around the cable, becomes visible. From its point of view, the ant can move forwards and backwards, and it can also move clockwise and counterclockwise.
So, dimensions can come in two varieties. They can be long and unfurled, like the length of the cable, but they can also be tiny and curled up, like the circular direction that wraps around it. Kaluza and Klein made the wild suggestion that the fabric of our universe might be kind of like the surface of the cable, having both big extended dimensions, the three that we know about, but also tiny curled up dimensions, curled up so tiny, billions of times smaller than even a single atom, that we just can't see them. And so our perception that we live in a universe with three spatial dimensions may not be correct after all. We really may live in a universe with more dimensions than meet the eye.
So, what would these extra dimensions look like? Kaluza and Klein proposed that if we could shrink down billions of times, we'd find one extra, tiny, curled-up dimension located at every point in space. And just the way an ant can explore the circular dimension that wraps around a traffic light cable, in theory, an ant that is billions of times smaller could also explore this tiny, curled-up circular dimension. This idea that extra dimensions exist all around us lies at the heart of string theory. In fact, the mathematics of string theory demand not one, but 6 extra dimensions, twisted and curled into complex little shapes that might look something like this.
If string theory is right, we would have to admit that there are really more dimensions out there. And I find that completely mind-blowing.
If I take the theory as we have it now literally, I would conclude that the extra dimensions really exist. They're part of nature.
When we talk about extra dimensions, we literally mean extra dimensions of space that are the same as the dimensions of space that we see around us. And the only difference between them has to do with their shape.
But how could these tiny extra dimensions, curled up into such peculiar shapes, have any effect on our everyday world? Well, according to string theory, shape is everything. Because of its shape, a French horn can produce dozens of different notes. When you press one of the keys, you change the note because you change the shape of the space inside the horn where the air resonates. And we think the curled-up spatial dimensions in string theory work in a similar way. If we could shrink down small enough to fly into one of these tiny, 6-dimensional shapes predicted by string theory, we would see how the extra dimensions are twisted and curled back on each other, influencing how strings, the fundamental ingredients of our universe, move and vibrate. And this could be the key to solving one of nature's most profound mysteries. In 1995, string theorists from all over the world gathered at the University of Southern California for their annual conference. Ed Witten showed up at Strings 95 and rocked their world.
I was really trying to think of something that would be significant for the occasion. And actually, since 5 string theories was too many, I thought I would try to get rid of some of them.
To solve the problem, Witten constructed a spectacular new way of looking at string theory.
Ed announced that he had thought about it, and moreover, he had solved it. He was going to tell us the solution to every string theory in every dimension. which was an enormous claim. But coming from Ed, it was not so surprising.
The atmosphere was electric because all of a sudden, string theory, which had been going through kind of doldrums, was given an incredible boost, a shot in the arm.
Ed Witten gave his famous lecture, and he said a couple of words that got me interested. And for the rest of the lecture, I got hooked up on the first few words that he said and completely missed the point of his lecture.
I remember I had to give the talk after him, and I was kind of embarrassed too.
Ed Witten just blew everybody away.
Ed Witten blew everybody away because he provided a completely new perspective on string theory. From this point of view, we could see that there weren't really 5 different theories. Like reflections in a wall of mirrors, what we thought were 5 theories turned out to be just 5 different ways of looking at the same thing. String theory was unified at last.
Witten's work sparked a breakthrough so revolutionary that it was given its own name, M theory, although no one really knows what the M stands for.
What is the M for?
M theory.
M theory.
M theory.
M theory.
M theory.
M theory is a theory.
I don't actually know what the M stands for.
Well, the M has...
I've heard many descriptions.
Mystery theory, magic theory.
It's the mother theory.
Matrix theory.
Monstrous theory. I don't know what Ed meant.
M stands for magic, mystery, or matrix, according to taste.
I suspect that the M is an upside-down W for Witten.
Some cynics have occasionally suggested that M may also stand for murky, because our level of understanding of the theory is in fact so primitive. Maybe I shouldn't have told you that one.
Whatever the name, it was a bombshell. Suddenly, everything was different.
There was a lot of panic, if you like, realizing that big things were happening and all of us not wanting to get left behind in this new revolution of string theory.
After Witten's talk, there was renewed hope that this one theory could be the theory to explain everything in the universe. But there was also a price to pay. Before M theory, strings seemed to operate in a world with 10 dimensions. These included 1 dimension of time, the 3 familiar space dimensions, as well as 6 extra dimensions, curled up so tiny that they're completely invisible.
Well, we think these extra dimensions exist because they come out of the equations of string theory. Strings need to move in more than 3 dimensions. And that was a shock to everybody, but then we learned to live with it.
But M theory would go even further, demanding yet another spatial dimension, bringing the grand total to 11 dimensions.
We know that there have to be 11 dimensions for this theory to make sense. So there must be 11 dimensions. We only see 3 plus 1 of them. How is that possible?
For most of us, it's virtually impossible to picture the extra higher dimensions. I can't. And it's not surprising. Our brains evolved sensing just the 3 spatial dimensions of everyday experience. So, how can we get a feel for them? One way is to go to the movies. We're all familiar with the real world having 3 spatial dimensions. That is, anywhere I go, I can move left, right, back, forth, or up, down. But in the movies, things are a bit different. Even though the characters on a movie screen look 3-dimensional, they actually are stuck in just 2 dimensions. There is no back, forth on a movie screen. That's just an optical illusion. To really move in the back, forth dimension, I'd have to step out of the screen. And sometimes moving into a higher dimension can be a useful thing to do. So, dimensions all have to do with the independent directions in which you can move. They're sometimes called degrees of freedom. The more dimensions or degrees of freedom you have, the more you can do. That's right. And if there really are 11 dimensions, then strings can do a lot more too.
People found fairly soon that there were objects that lived in these theories, which weren't just strings, but were larger than that. They actually looked like membranes or surfaces.
The extra dimension Witten added allows a string to stretch into something like a membrane, or a brain for short. A brain could be three-dimensional, or even more. And with enough energy, a brain could grow to an enormous size, perhaps even as large.
These theories, which weren't just strings, but were larger than that. They actually looked like membranes or surfaces.
The extra dimension Witten added allows a string to stretch into something like a membrane, or a brain for short. A brain could be three-dimensional, or even more. And with enough energy, a brain could grow to an enormous size, perhaps even as large as a universe. This was a revolution in string theory.
String theory has gotten much more baroque. I mean, now there are not only strings, there are membranes. People go on calling it string theory, but the string theorists are not sure it really is a theory of strings anymore.
The existence of giant membranes and extra dimensions would open up a startling new possibility. That our whole universe is living on a membrane inside a much larger, higher dimensional space. It's almost as if we were living inside a loaf of bread. Our universe might be like a slice of bread, just one slice in a much larger loaf that physicists sometimes call the bulk. And if these ideas are right, the bulk may have other slices, other universes that are right next to ours, in effect, parallel universes. Not only would our universe be nothing special, but we could have a lot of neighbors. Some of them could resemble our universe. They might have matter and planets and, who knows, maybe even beings of a sort. Others could certainly be a lot stranger. They might be ruled by completely different laws of physics. Now, all of these other universes would exist within the extra dimensions of M-theory, dimensions that are all around us. Some even say they might be right next to us, less than a millimeter away. But if that's true, why can't I see them or touch them?
If you have a brain living in a higher dimensional space and your particles, your atoms, cannot get off the brain, it's like trying to reach out, but you can't touch anything. It might as well be on the other end of the universe.
And it's a very powerful idea, because if it's right, it means that our whole picture of the universe is clouded by the fact that we're trapped on just a tiny slice of the higher dimensional universe. And it's a very powerful idea, because if it's right, it means that our whole picture of the universe is clouded by the fact that we're trapped on just a tiny slice of the higher dimensional universe.
It is a powerful idea, especially because it may help solve one of the great mysteries of modern science. It has to do with gravity.
It's been more than 300 years since Isaac Newton came up with the universal law of gravity, inspired, as the story goes, by seeing an apple fall from a tree. Today it seems obvious that gravity is a powerful force.
It would seem to most people that gravity is a very important force. It's very strong. It's very hard to get up in the morning, stand up, and when things fall, they break because gravity is strong. The fact of the matter is that it's not strong. It's really a very weak force.
Gravity pulls us down to the Earth and keeps our Earth in orbit around the sun. But in fact, we overcome the force of gravity all the time. It's not that hard. Even with the gravity of the entire Earth pulling this apple downward, the muscles in my arm can easily overcome it. And it's not just our muscles that put gravity to shame. Magnets can do it too, no sweat. Magnets carry a different force, the electromagnetic force. That's the same force behind light and electricity. It turns out that electromagnetism is much, much stronger than gravity. Gravity, in comparison, is amazingly weak. How weak? The electromagnetic force is some 1,000 billion times stronger. That's a 1 with 39 zeros following it. The weakness of gravity has confounded scientists for decades. But now, with the radical world of string theory, filled with membranes and extra dimensions, there's a whole new way to look at the problem.
One way of approaching the question of why gravity is so weak compared to all the other forces is to turn the question completely on its head and say, no, actually, gravity isn't very weak compared to all the other forces. It just appears to be weak.
It may be that gravity is actually just as strong as electromagnetism, but for some reason, we can't feel its strength.
Consider a pool table, a very large pool table. Think of the surface of the pool table as representing our three-dimensional universe, although it is just two-dimensional. And think of the billiard balls as representing atoms and other particles that the universe is made out of.
So here's the wild idea. The atoms and particles that make up stuff in the world around us will stay on our particular membrane, our slice of the universe, just as the billiard balls will stay on the surface of the pool table. Unless you're a really bad pool player. But whenever the balls collide, there is something that always seeps off the table. Sound waves. That's why I can hear the collision. Now, the idea is that gravity might be like the sound waves. It might not be confined to our membrane. It might be able to seep off our part of the universe. Or think about it another way. Instead of pool tables, let's go back to bread. Imagine that our universe is like this slice of toast, and that you and me and all of matter, light itself, everything we see, is like jelly. Now, jelly can move freely on the surface of the toast, but otherwise it's stuck. It can't leave the surface itself. But what if gravity were different? What if gravity were more like cinnamon and sugar? Now, this stuff isn't sticky at all, so it easily slides right off the surface. But why would gravity be so different from everything else that we know of in the universe? Well, it turns out that string theory, or M theory, provides an answer. It all has to do with shape. For years, we concentrated on strings that were closed loops, like rubber bands. But after M-theory, we turned our attention to other kinds. Now we think that everything we see around us, like matter and light, is made of open-ended strings. And the ends of each string are tied down to our three-dimensional membrane. But closed loops of string do exist, and one kind is responsible for gravity. It's called a graviton. With closed loops, there are no loose ends to tie down, so gravitons are free to escape into the other dimensions, diluting the strength of gravity and making it seem weaker than the other forces of nature. This suggests an intriguing possibility.
If we do live on a membrane, and there are parallel universes on other membranes near us, we may never see them, but perhaps we could one day feel them through gravity.
If there happens to be intelligent life on one of the membranes, then this intelligent life might be very close to us. So theoretically, and purely theoretically, we might be able to communicate with this intelligent life by exchanging strong gravity wave sources. Then this intelligent life might be very close to us. So theoretically, and purely theoretically, we might be able to communicate with this intelligent life by exchanging strong gravity wave sources.
So who knows, maybe someday we'll develop the technology and use gravity waves to actually communicate with other worlds. Yeah, hey, it's Brian. How you doing?
Brian. Jabby Woofalabba Jabba Simpsons.
We don't really know if parallel universes could have a real impact on us. But there is one very controversial idea which says they've already played a major role. In fact, it gives them credit for our existence.
As the classic story goes, the vast universe we see today was once extremely small, unimaginably small. Then, suddenly, it got bigger. A lot bigger during the dramatic event known as the Big Bang. The Big Bang stretched the fabric of space and set off the chain of events that brought us to the universe we know and love today. But there's always been a couple of problems with the Big Bang theory. First, when you squeeze the entire universe into an infinitesimally small but stupendously dense package, at a certain point, our laws of physics simply break down. They just don't make sense anymore.
The formulas we use start giving answers that are nonsensical. We find total disaster. Everything breaks down, and we're stuck.
And on top of this, there's the bang itself. What exactly is that?
That's actually a problem. Classic form of the Big Bang theory really says nothing about what banged, what happened before it banged, or what caused it to bang.
Refinements to the Big Bang theory do suggest explanations for the bang, but none of them turn the clock back completely to the moment when everything started.
Most people come at this with the naive notion that there was a beginning, that somehow space and time emerged from nothingness into somethingness.
Well, I don't know about you, but I don't like nothing. Do I really believe that the universe was a big bang out of nothing? And I'm not a philosopher, so I won't say, but I can imagine to a philosopher that is a problem. But to a physicist, I think it's also a problem.
Everyone admits there are problems. The question is, can string theory solve them? Some string theorists have suggested that the Big Bang wasn't the beginning at all, that the universe could have existed long before, even forever. Not everyone is comfortable with the idea.
I actually find it rather unattractive to think about a universe without a beginning. It seems to me that a universe without a beginning is also a universe without an explanation.
So what is the explanation? What if string theory is right, and we're all living on a giant membrane inside a higher dimensional space?
One of the ideas in string theory that was particularly striking to me and suggested perhaps a new direction for cosmology is the idea of brains and the idea of brains moving in extra dimensions.
Some scientists have proposed that the answer to the Big Bang riddle lies in the movements of these giant brains.
It's so simple. Here's a brain on which we live, and here's another brain floating in the higher dimension. There's absolutely nothing difficult about imagining that these collide with each other.
According to this idea, sometime before the Big Bang, two brains carrying parallel universes began drifting toward each other until
all of that energy has to go somewhere. Where does it go? It goes into the Big Bang. It creates the expansion that we see, and it heats up all the particles in the universe in this big fiery mass.
As if this weren't weird enough, the proponents of this idea make another radical claim. The Big Bang was not a special event. They say that parallel universes could have collided not just once in the past, but again and again. And that it will happen in the future. If this view is right, there's a brain out there right now headed on a collision course with our universe.
So another collision is coming, and there'll be another Big Bang, and this will just repeat itself for an indefinite period into the future.
It's an intriguing idea. Unfortunately, there are a few technical problems.
Well, that was a very ingenious scenario that arose naturally within string theory. However, the good old problems creep back in again.
The fact is, we don't really know what happens when two brains collide. You can wind up with the same situation we had with the Big Bang. The equations don't make sense.
They have to make a lot of assumptions in their models, and I don't think they've really solved the problem of the Big Bang in string theory.
If string theory is the one true theory of the universe, it will have to solve the riddle of the Big Bang. And there's a lot of hope that someday string theory will succeed. But for now, there's also a lot of uncertainty. As promising and exciting as the theory is, we don't entirely understand it.
It's as if we've stumbled in the dark into a house, which we thought was a two-bedroom apartment, and now we're discovering is a 19-room mansion, at least, and maybe it's got 1,000 rooms, and we're just beginning our journey.
So how sure are we that the universe is the way that string theory describes it? Is the world really made up of strings and membranes, parallel universes, and extra dimensions? Is this all science or science fiction?
Well, the question we often ask ourselves as we work through our equations is this just fancy mathematics, or is it describing the real world?
These exercises in our imagination and mathematics are all, at the end of the day, subjected to a single question. Is it there in the laboratory? Can you find its evidence?
String theory and string theorists do have a real problem. How do you actually test string theory? If you can't test it in the way that we test normal theories, it's not science, it's philosophy. And that's a real problem.
Strings are thought to be so tiny, much smaller than an atom, that there's probably no way to see them directly.
But even if we never see strings, we may someday see their fingerprints. You see, if strings were around at the beginning of the universe, when things were really tiny, they would have left impressions or traces on their surroundings. And then, after the Big Bang, when everything expanded, those traces would have been stretched out along with everything else. So if that's true, we may someday see the telltale signs of strings somewhere in the stars. But even here on Earth, there's a chance we can detect evidence of strings. This past year in Illinois, but even here on Earth, there's a chance we can detect evidence of strings. This past year in Illinois serves as command central for a lot of this research. Well, actually, the real work happens underground, where the hunt is on for evidence supporting string theory, including extra dimensions.
Not too many years ago, people who talked about large extra dimensions would have been considered crackpots, to put it lightly.
But all that has changed thanks to string theory. This is Fermilab, and right now, it's our best hope for proving that extra dimensions are real. Fermilab has a giant atom smasher. Here's how it works. Scientists zap hydrogen atoms with huge amounts of electricity. Later, they strip them of their electrons and send the protons zooming around a 4-mile circular tunnel beneath the prairie. Just as they're approaching the speed of light, they're steered into collisions with particles whizzing in the opposite direction. Most collisions are just glancing blows, but occasionally there's a direct hit. The result is a shower of unusual subatomic particles. The hope is that among these particles will be a tiny unit of gravity, the graviton. Gravitons, according to string theory, are closed loops, so they can float off into the extra dimensions. The grand prize would be a snapshot of a graviton at the moment of escape.
And then the graviton goes to the extra dimension, and then it shows in the detector by its absence. You see it by its absence.
Unfortunately, Fermilab hasn't yet seen the vanishing graviton. And the pressure is on, because another team is hot on the same trail. "4,000 miles away, on the border of France and Switzerland, a lab called CERN is constructing an enormous new atom smasher. When it's finished, it will be 7 times more powerful than Fermilab's.
There's a great sense of urgency that every minute has to count, but eventually CERN, our rival laboratory, will, frankly, blow us out of the water.
CERN will blow Fermilab out of the water not only in the search for extra dimensions, but other wild ideas. At the top of the to-do list for both labs is the hunt for something called supersymmetry. That's a central prediction of string theory, and it says in a nutshell that for every subatomic particle we're familiar with, like electrons, photons, and gravitons, there should also be a much heavier partner called a sparticle, which so far no one has ever seen. Now, because string theory says sparticles should exist, finding them is a major priority.
So it's a big discovery to find supersymmetry. That's a humongous discovery, and I think it's a bigger discovery to find supersymmetry than to find life on Mars.
If we were to hear tomorrow that supersymmetry was discovered, there would be parties all over the planet.
The problem is, if they exist, the sparticles of supersymmetry are probably incredibly heavy. So heavy that they may not be detected with today's atom smashers. The new facility at CERN will have the best chance once it's up and running in several years. But that won't stop the folks at Fermilab from trying to find them first.
The competition is friendly and fierce at the same time. We're competing like bad dogs, essentially. And it has always been like that, and it will always be like that.
We have to make sure that we don't make any mistakes, that we do absolutely the best we can do with these experiments, and take advantage of what is really one of the great golden opportunities for discovery.
If we do find sparticles, it won't prove string theory, but it will be really strong circumstantial evidence that we're on the right track. Over the next 10 to 20 years, the new generation of atom smashers is sure to uncover surprising truths about the nature of our universe. But will it be the universe predicted by string theory? What if we don't find sparticles or extra dimensions? What if we never find any evidence that supports this weird new universe filled with membranes and tiny vibrating strings? Could string theory, in the end, be wrong?
Oh yes, it's certainly a logical possibility that we've all been wasting our time for the last 20 years and that the theory is completely wrong.
There have been periods of many years where all of the smart people, all of the cool people were working on one kind of theory, moving in one kind of direction, and even though they thought it was wonderful, it turned out to be a dead end. This could happen to string theory.
Even though there's no real evidence yet, so much of string theory just makes so much sense. A lot of us believe it's just got to be right.
I don't think it's ever happened that a theory that has the kind of mathematical appeal that string theory has turned out to be entirely wrong. I would find it hard to believe that that much elegance and mathematical beauty would simply be wasted.
I don't really know how close we are to the end. You know, are we almost there and having the complete story? Is it going to still be another 10 years? Nobody knows. I think it's going to keep me busy for a long time.
We have been incredibly lucky. Nature has somehow allowed us to unlock the keys to many fundamental mysteries already. How far can we push that? We won't know until we try.
A century ago, some scientists thought they had pretty much figured out the basic laws of the universe. But then Einstein came along and dramatically revised our views of space and time and gravity. And quantum mechanics unveiled the inner workings of atoms and molecules, revealing a world that's bizarre and uncertain. So, far from confirming that we had sorted it all out, the 20th century showed that every time we looked more closely at the universe, we discovered yet another, unexpected layer of reality. As we embark on the 21st century, we're getting a glimpse of what may be the next layer. Vibrating strings, sparticles, parallel universes, and extra dimensions. It's a breathtaking vision, and in a few years, experiments may begin to tell us whether some of these ideas are right or wrong.
But regardless of the outcome, we'll keep going because, well, that's what we do. We follow our curiosity. We explore the unknown. And 100 or 1,000 years from now, today's view of the cosmos may look woefully incomplete, perhaps even quaint. But undeniably, the ideas we call string theory are a testament to the power of human creativity. They've opened a whole new spectrum of possible answers to age-old questions. And with them, we've taken a dramatic leap in our quest to fully understand this elegant universe.